from Bilinear University, who also moonlights as associate secretary of the AMS, who will speak about the adjoint operator.
Okay.
And usually we're going to take the speaker to the usual place. If you'd like to join us for dinner, please let me know immediately after the talk.
Okay, so thanks very much for the invitation to speak here. And I want to talk about a particular example of an adjoint, a beautiful example that should have been computed 100 years ago, but seems to have been entirely overlooked. So what I want to look at is the following. Let's consider the vector space of polynomials of degree at most n for some fixed n. Then we have the very natural inner product. The inner product of f and g is the integral from 0 to 1 of their product, so it's just the L2 norm restricted to this. So we have this vector space with this non-singular inner product, and we have the operator of differentiation, right? The derivative of d of f is its derivative, and we'd like to ask what the adjoint d star of d is. And particularly, what we ask is we'd like to concretely figure out what a formula for the adjoint is. Okay, so let's begin with some, and I should say here that I do need to thank Duran for a crucial suggestion in this, which I will explain when I get to the right point in the talk. Okay, so let's begin with some background here. So we begin with a vector space and a bilinear form on V. Then the form is symmetric if VW is WV for any pair of vectors. It's non-singular if the only vector W such that VW is always 0 is the 0 vector W. And it's positive definite if any vector V against itself is positive, except for the 0 vector. And of course, positive definite implies non-singular, since if W is not 0, then WW isn't 0. So one way of getting bilinear forms is you can start with an n by n matrix A, and then you can look at the bilinear form on Rn given by V comma W is the transpose of V times A times W. And in terms of matrices, the form is symmetric if the matrix is symmetric equal to its transpose. The form is non-singular if the matrix is non-singular in the usual sense, that is invertible, and positive definite is exactly the definition of a positive definite matrix. And in fact, it's easy to see that every bilinear form on Rn arises in this way. In fact, not only does every bilinear form on Rn arise in this way, but every bilinear form on a finite dimensional vector space essentially arises in this way. And what I mean by essentially is after taking coordinates. So let me just remind you about coordinates. So suppose we pick a basis B for our vector space V, and we fix the basis. Then we have the coordinate vector of a vector V with respect to the basis B. That's just, we express V as a linear combination of basis elements, and we just take the coefficients. Similarly, if we have a linear transformation T from V to V, it has a matrix in the basis B, and this is the usual formula for the matrix. So those are very well known. What's perhaps a little less well known, since people don't study bilinear forms quite as often, is that we also have the matrix of a bilinear form. So suppose, again, we have this fixed bilinear form, and we have a fixed basis. Then the bilinear form is matrix A, whose typical entry Aij is the value of the bilinear form on the pair Bi comma Bj. Okay? And then in this situation here, so we have our vector space V, we've picked the basis of B, and we pick the basis B of V, then the inner product of V and W is the transpose of V, we take the coordinate vector of V, we take the transpose of that times the matrix A sub B times the coordinate vector of W. And so the form is given by this here. And conversely, if we start with any matrix, if we start with any matrix AB, we get a form. So this is exactly how we get forms, is after taking coordinates, it's the same formula we had above. Okay, now we want to bring in the dual space. Remember that the dual space of a vector space is the vector space of linear transformations F from V to R. So we're looking at real vector spaces, but in fact, in this talk, nothing would change if we were looking at complex vector spaces. So for simplicity, we'll just consider real vector spaces. And as is well known, if V is a finite dimensional vector space of dimension n, then its dual space V star is also n-dimensional. Okay, now here's a construction we're going to need. Suppose we fix a non-singular bilinear form on our vector space V, which is finite dimensional. and that's going to be crucial as we'll see, then we look at any element f in v star. So any function, any linear transformation from v to r is given as follows. F of v is the inner product of v with x for some fixed vector x in v. So let's prove this, so let's consider mapping S from V to V star given as follows. So V star is linear transformations from V to R. So S of X is going to be a linear transformation from V to R. So I have to tell you what the value of S of X is on a typical vector V. And the answer is that S of X of V is V comma X, where this is my inner product. The bilinearity of the form says that both this is a linear transformation and the map S from V to V star is a linear transformation. So, and now we have the condition of non-singularity, and non-singularity is exactly what we need for this map S to be injective. Because what does it mean to say that S of X is 0? It means it's the 0 function. So that says that S of X is V is 0 for every vector V. Well, S of X of V is just this. That says Vx is 0 for every vector V, and that's exactly the condition of non-singularity that only happens for x equals 0. So we have a linear transformation between vector spaces of the same dimension. So in elementary linear algebra, dimension count says that if it's injective, it's surjective as well. So f is S of X for some unique vector x, right? So f of v is v comma x. So notice this proof works in the finite dimensional case because we can do dimension counting. In the infinite dimensional case, we still have the map is injective. That argument still works, but we can't conclude anything about surjectivity because we don't have dimension count. But if x, injectivity says if x exists, it's unique, but x may or may not exist. Okay, so let's now continue. So now we still have our vector space V with a fixed non-singular form on it, and we now consider a linear transformation. We now consider a linear transformation T from V to itself. So we fix a vector W in V, and now we define the following element in the null space. So that's a linear transformation from V to R, and it's defined by f sub W of V is the value of the inner product T of V comma W. So this is an element in the dual space. So by exactly this previous lemma here, right, we have some element in the dual space. Either there is a unique such x such that f of v is v comma x, or no such x exists. All right, so either f sub w of v is v comma x for some unique x, or no such x exists. And suppose that x always does exist. Then in this situation, we define the adjoint of t, t star, by t star of w equals x. In other words, t star is defined implicitly by this equation, v comma t star of w equals t of v comma w. And what this previous lemma says is that this implicit equation actually gives me a well-defined vector x. So this implicit equation defines x for me. And in this case, and as we said, in the finite dimensional case, the x always exists. So in the finite dimensional case, no matter what linear transformation t we start with, t always has an adjoint. And in fact, that's what we call the adjoint here. The adjoint is defined by t star of w equals x. So this implicit equation is defining the adjoint. Okay, and in the finite dimensional case, not only do we have the adjoint defined, but we can also easily calculate it. So here's how we calculate it. So what I'm going to think of is I start with v. Again, I have to pick a basis so that I can use coordinates. I have my fixed form, and I suppose that I know the matrix of the form, A. I suppose that I know the matrix M of t, again with respect to this basis, and I want to find the matrix N of t star. Then N is simply given by this equation. N is A inverse times the transpose of M times A. And this is straightforward to prove. Here's the identity that defines t star. So if we translate this into coordinates, if y is the coordinate vector here and z is the coordinate vector here, that's just the identity. Y comma nz is my comma z, where n is the mysterious matrix I'm trying to find, and m is the one I know. Well, by the definition of the inner product is is the transpose of the first guy times A times the second guy. So that's true here, and that's true here. Right? And so we get this equation here. The transpose of y times A times n times z is the transpose of y times the transpose of m times A times z. And this has to be true for any two vectors y and z. So that means that the matrix A times n must be transpose of m times A, and we solve for n, and we get n equals A inverse times the transpose of m times A. So exactly the formula here. Now I will remark here something that is not the case we're interested in, but it's often the case that if you think about the dot product, and you have the standard basis, then A is the identity matrix, so in that case you get that n is the transpose of m. So sometimes people will say, well, transpose is just adjoint, but that's only in this case or in the case where you have an orthonormal basis. But in general, the transpose is given, the adjoint is given by this more interesting formula. Okay, so with all these remarks, let's do an example. Let's start here with considering the space of either all real C infinity functions on 0, 1 or the space of all polynomials on 0, 1. So we have this vector space, and we'll look at this inner product. Inner product of f and g is the integral from 0 to 1 of f of x times g of x dx. And we'll look at the differentiation operator. Okay. Well, this is an infinite dimensional vector space, so from what I've said before, D may or may not have an adjoint. And in fact, in this case, D does not have an adjoint. This is a well-known result. I guess well-known to those who know it well, as the saying goes, but it's certainly a known result. But let me prove it for you anyway. It's an instructive proof and an idea we're going to use later. So the proof is by contradiction. Let's suppose we had an adjoint D star, and let's consider the operator H equals D plus D star. So if H is D plus D star is minus D plus H. Okay. So let's look at this string in the clause. So here's just the definition of the adjoint. Okay. D star is minus D plus H, so D star of G is minus G prime plus capital H. So let's solve for the inner product here. The inner product of f of x with capital H of G of x is f prime of x with G of x plus f of x with G prime of x. Well, my inner product is just given by this integral. So this is the integral of f prime of x G of x plus the integral of f of x G prime of x. We simply add them, and now we notice we're doing integration by parts backwards. This is just the derivative of the product. So we apply the fundamental theorem of calculus to say that this integral is simply the product evaluated between 1 and 0. So that's f of 1 times g of 1 minus f of 0 times g of 0. Okay. So what I'm going to do now is I'm going to adopt the viewpoint that g of x is going to be fixed. And if g of x is fixed, I'll let little h of x be capital H of g of x. And then I'll think of f of x as a test function k of x. So just rewriting this here, if little g of x is fixed and little h of x is capital H of g of x, I get that k of x h of x is k of 1 g of 1 minus k of 0 g of 0. Okay. So g of x is going to be fixed. So let's look at the function g of x equal x. Okay, so we look at that function here, and here's little h of x. And let's take the function k of x equal x as well. So when we look at them, we get that this inner product here is k of 1 g of 1 minus k of 0 g of 0. So k and g are both the function x, so this is 1 times 1 minus 0 times 0, so that's equal to 1. So in particular, since k of x evaluates non-zero against h of x is not the zero function. On the other hand, let's keep g of x to be little x, so h of x is still the same. But now let's try k of x is x squared times x minus 1 squared times h of x. Okay? Then, on the one hand, if we look at the same thing, we get k of 1 times g of 1 minus k of 0 times g of 0. But I've set up this function here so that k vanishes at both 0 and 1. So regardless of what, so we get the k of 0 and k of 1 is 0, so this answer is 0. So on the one hand, we get this answer is 0. But on the other hand, if we actually evaluate this from the definition, we get that this integral is the integral of k of x times h of x, and when we multiply k of x times h of x, we simply get the integral of this, and this is a square. Right? It's a square. It's not identically 0 because h of x is non-zero, so there's somewhere it's not 0. So we have a square, and the integral of a square is integral of something positive is always positive. So we have a contradiction. Right? And since we have a contradiction, then d star cannot exist. Okay, so in this case, we do not have an adjoint, but that was the case of all polynomials, so that brings us to say, instead of considering all polynomials, let's restrict to the space of polynomials of degree at most n for any fixed n. So that's a finite dimensional vector space, so in the finite dimensional case, we always have an adjoint. And so that's going to be the object of this talk, to find out what the adjoint is. But one thing I should say is, if you think about the derivative of a polynomial doesn't depend what space you're in. Right? So you might think that the adjoint shouldn't depend what space you're in either, but that's false. The adjoint depends very much on what space we're in. Okay, so how are we going to compute the adjoint? Well, since the adjoint is a linear transformation, so in order to find what d star is, we merely have to find out what it is on some basis. So we'll choose the standard basis for the space of polynomials of degree n, namely 1x, x squared, up to x to the n. Okay? So if we think about this basis, we're going to use this proposition. Right? So what does it say I have to compute? Well, first of all, it says I have to compute the matrix of D in this case. Well, the matrix of T is really easy because D is differentiation, right? The derivative of x to the k is kx to the k minus 1. The other thing I have to compute is the matrix A of this linear transformation. Okay, so let's go ahead and compute that. So in order to compute that, I have to evaluate a pair of basis vectors against each other. So I take the value of xi against xj. By definition, that's the integral of their product. That's x to the I plus j plus 1 over I plus j plus 1 from 1 to 0. That's 1 over I plus j plus 1. So the matrix in this basis is simply the matrix whose entry in the ij position is 1 over I plus j plus 1. Except that we're numbering not as usual, starting with row in column 1, but with row in column 0, right? Because the first power there is x to the 0. So we have this numbering here where the rows and columns are numbered 0 through n. So in other words, the 0th row, the top row of this matrix is 1, a half, a third, a quarter, a fifth. The next row is a half, a third, a quarter, a fifth, a sixth, a third, a quarter, a fifth, a sixth, a seventh, etc. And this is a very well-known matrix. It's the n plus 1 by n plus 1 Hilbert matrix. So that's our matrix A. The formula also involves A inverse. Well, A is a well-known matrix, and A inverse is also known. Okay, so what did I do? I did a numerical experiment. I wrote a computer program to compute what d star is for small values of n, small in this case being n, running from 0 to 7. So let me show you my computer output. Okay, here's my computer output. Okay, let's, well, in the case n is 0, differentiation is a 0 operator, so is its adjoint. But here's a typical example. So in this computer program, I fixed A and I allowed myself to choose any linear transformation here. So here's the matrix of differentiation, right? So what does this mean? Well, the first element in my vectors, the first element of my basis is 1. So d of 1 is 0 times 1 plus 0 times x plus 0 times x squared. Right? The next element is x, so d of x is 1 times 1 plus 0 times x plus 0 times x squared. And then the next one is x squared, its derivative is 0 plus 2 times x plus 0 times x squared. Right? And then here's the matrix of the adjoint. Well, I looked at this and there was something very surprising about this. And that is the 0, so I'm numbering from 0 to n, the 0th column is whatever it is. Right? But all the other columns are almost identical. That really surprised me when I saw it, right? If you look at this column and this column, well, this column, this column, this column, this column, they're all, the first entries are all the same. They're all 5, except that one's 1 less. The second entries are all the same, except that one's 2 less. The third entries are all the same, except that one's 3 less. The fourth entries are all the same, except that one's 4 less, and the last entries are all the same. Similarly here, right? Look at this case, same thing. The first entries are all the same, except this is 1 less. The second entries are all the same. Actually, I guess the 0th entries are all the same, except this is 1 less. The next entries are all the same, except this is 2 less. The next entries are all the same, except this is 3 less. So, morally speaking, there are only 2 columns to this matrix. There's the column at the start, and then there's one other column that gets modified slightly to give you all the other columns. Okay. Now, that's the first thing you notice. The second thing you notice is if you look at these columns here, they change as you go from one value of n to the next, as you would expect. But if you look at this guy up in front, he only changes every other time, right? This is really representing the polynomial minus 20 plus 180x minus 420x squared plus 280x cubed. And this one is representing minus 20 plus 180x plus 420x squared plus 280x cubed plus 0x to the fourth. Right? So we're really getting the same answer twice in a row, and then we change. And then finally, you see that there's an obvious alternation of sign in this matrix. Okay, so we have this matrix here, and we'd like to figure out what all these entries are. Okay, so first of all, let me state a theorem. Now, at this point, the theorem is only a conjecture, but everything I'm going to say turns out to be true. Okay, so here's the first thing in our first basis of on our basis of our numerical evidence. Here's the first thing we conjecture. For any n greater than 0, there are exactly two polynomials, Qn of x and Rn of x, such that d star is given as follows: d star of 1 is Qn of x. That's not really a theorem. That's just giving the 0th column a name. This is really the theorem. There's this one other polynomial, R sub n of x, such that for every value of k between 1 and n, d star of x to the k is minus kx to the k minus 1 plus R sub n of x. Right? This is sort of the little correction that prevents all the other columns from being the same, and this is the sort of the common value of all the other columns that get slightly modified. Okay, and then once you have this, then it's easy to express what the derivative is in terms of these polynomials. If you just let it, you're getting a0 times this guy, and then you're getting. Notice that this is minus the derivative, right? Here for each one of these basis vectors, and for 1 you also have minus the derivative. That's a 0 there, you just don't see it. So if we take d of g of x, it's minus g prime of x plus a0 times this guy plus the sum of all the other coefficients times this guy, Rn of x. Okay, so we have this theorem, but this theorem is only going to be a good theorem if we can actually figure out what the polynomials Qn of x and Rn of x are. Okay? So that's what we want to do next. We want to figure out what Qn of x and Rn of x are. And I'm going to concentrate on Rn of x. The ideas for Qn of x are the same, but I figured out Rn of x first, and I'll just tell you how to do that. Okay. So what I decided was to do the following. I said, let's look at the coefficients here. First of all, I said there's an alternation of sign, so let's just put that sign in to remove the alternation. And then here are the other coefficients. So for example, here, right, here will be, let's see, for n equals 5, here's R5. It's 5 minus 120x plus 630x squared minus 1120x cubed plus 630x to the fourth. Oh, I guess that's for n equals 4. So, okay? And these are only defined for n greater than or equal to 1, so there's nothing defined there, but we're doing experiments, and obviously I should continue this matrix like that. So here I have this matrix, triangular matrix, because the coefficients I go from 0 to n. So I have this triangular matrix where each column represents the coefficients of my mysterious polynomial R sub n. And again, we're proceeding experimentally. I decided to look at the high order coefficients, the ones along the diagonal. Okay. So here we are, and I decided that these numbers should have some numerical significance. They're all integers. Well, we thank God for primes. For the small guys, there are so many factors it's a little hard to see, but primes don't appear by accident, and actually the first one I looked at is this one. 2772 is divisible by 11. So, right? Okay, well, 2772, okay, well then the next one, you see that 140 is divisible by 7, well, that's a small number, that could be an accident, but the next one, 12,012, a very unlikely number, is divisible by 13. Right? So now something is really up. Sure enough, if you look at all these numbers, you get this same pattern. So the conjecture forces itself upon us that all of these numbers, that the highest coefficient of R sub n is divisible by 2n plus 1. Okay. So we not only want to find out what it's divisible by, we want to find out what it is equal to exactly. Okay, so let's again go back to this guy, alpha 5. He's divisible by 11, so here's the quotient, 252. Okay, again, we try to factor things. 252 is 9 times 7 times 4. That's a slightly ridiculous factorization. It's much more sensible to make that 9 times 8 times 7 over 2. Okay? Now 10 is missing, so we'll put that in. We'll get 11 times 10 times 9 times 8 times 7 over 5 times 4. Well, now this is just sort of begging us to finish. And so we finish with 11 times 9, right? We finish with putting a factor of 6 in the numerator and 3 times 2 times 1 in the denominator. Okay? And then once we've got that, we just rewrite it like that. We just rewrite it like that. Okay, so that worked for 2772. We'll try the same thing for, and I should observe that that is 11 choose 5 times 6. That worked fine for 2772. If we try for alpha 3, we get 7 choose 3 times 4, following the pattern. If we try for the next one, alpha 6, we get 13 choose 6 times 7. So again, within this range of the table, we have this pattern here. And so the conjecture forces it upon us that the highest coefficient, Cnn, is given by 2n plus 1 choose n times n plus 1. Right? That's what we have here. Okay, so we've determined the high order coefficient of this guy. Now we'd like to determine all the coefficients. So we go back to this, this triangular matrix and we have a look. Well, remember that the coefficients go in the columns. And if you look at the columns, that doesn't look so helpful. There's no obvious relation between 2772 and the other entries here. And there's no obvious relation. There's no obvious relation between the diagonal and the other entries in its column. So we stare at this matrix a little longer. And if we stare at this matrix a little longer, we see that there's no obvious relation between what's going on in the columns, but on the other hand, the diagonal entry divides every other entry in its row. Right? These two guys are multiples of 2772, these guys are multiples of 630, etc. Okay? So now we think we're onto something, so we'll divide out by that factor. Okay, we divide out by that factor and we see these numbers. Okay? We want to make sense of these numbers, so we stare at them hard enough, and once we stare at them hard enough, we see that they're given as follows. Okay? So they're always binomial coefficients. You see if we're 1 above the diagonal, the denominator is a choose 1. If we're 2 above the diagonal, the denominator is a choose 2, etc. And if you look at the sum of these, it's always 2n plus 1. 12 plus 1, 11 plus 2, 10 plus 3, 13. So putting all this together, we now conjecture, and we will later prove, that the coefficients of the polynomial r sub n of x are given by here's the sign, and then it turns out to just be this. Well, as I've said, concentrating on the Rn, but once you get the idea to do this, then you can try doing this for the Qn, and the Qn has a sort of similar formula. We get a different alternation of sign here. These two factors are the same. Instead of an I plus 1, we have an n minus I. That's an even case, and then, as I said, we only change every other time. So that's, for n is odd, it's the next higher even value. Okay, so we'd like to prove this theorem, and how are we going to prove this theorem? Well, we're going to bring a new part of a bunch of new actors into the play at this point. And the new actors that come in are the classical Legendre polynomials. So these are a classical sort of orthogonal polynomials. The most classical Legendre polynomials are on the interval -1, 1. And then there's the classical shifted Legendre polynomials. There, the Legendre polynomial is shifted to the interval 0. So I'm going to call them pk star of x. In terms of the most classical ones, they're pk of 2x minus 1. And the basic property of the Legendre polynomials is that, well, first of all, the polynomial pk star of x is degree k. So if we look at the set of polynomials from p0 star to pn star, right, we have polynomial of each degree from 0 to n. That's the basis of V, which is the space of polynomials of degree at most n. But the key point about this basis, the reason that Legendre polynomials exist in the first place, is that this is an orthogonal basis with respect to our inner product. So orthogonal means the inner product we've been considering all along. So what orthogonal means is if I take pi star comma pj star, I get 0 for I not equal to j. But it's orthogonal and not orthonormal. It's not the case that pk star is 1. It's that pk star evaluated against pk star is 1 over 2k plus 1. So these are very classical facts about the shifted Legendre polynomials. And here are some other facts. The value of all of these at 1 is 1. The value at 0 is minus 1 to the k. And furthermore, these are well-known polynomials, right? Legendre lived 200 years ago. So here's an explicit expression for the coefficients of pk star of x.